Yep. Good morning, everyone. My name's Sam Smith. My talk is on the gallery. Sorry, put the water down. Galleries to Calories project. So I'll start by just giving a bit of a background to the project as a whole. Talk briefly about the supply and demand assessment. Then the interesting bit, which is the economics of this project, and then finally finish on sort of where we're hoping to go next with this research. So Galleries to Calories, or G2C, it aims to demonstrate the use of legacy mine workings, so the galleries, to store and transport waste heat from data centers. So that's the calories aspect. Data centers, this is particularly topical at the moment because data centers, as we all know, use a very large and increasing amount of global electricity, which leads to a high cost of cooling for those operators to keep the IT equipment at suitably cool temperatures. But this also provides a huge potential waste heat source, as we've heard, to heat homes and businesses and potentially reduce fuel poverty. So this is the idea of the geobattery concept, and the case study for this work is the University of Edinburgh's Advanced Computing Facility, or the ACF, which hosts the Archer 2 research supercomputer. And you can see where it is on the map here to the south of Edinburgh in the county of Midlothian, and in purple there you can see the extensive sort of Victorian mine workings underlying the site. So the first step is to understand the supply and also where the heat demand is. So the ACF is currently a 6 megawatt data center with producing heat at 32 degrees all year round. And in terms of the demand, we identified two potential heat networks. The first is centered around the Easterbush University campus, where the ACF is located. And there's a second that we identified to the north in the village of Lonehead, and you can see the sort of anchor loads identified in the red dots there. And we calculated the annual and peak demand, which you can see in the table there. We, as part of another work package of the project, we modelled the University of Edinburgh modelled the spatial distribution of a plume injected into the mine workings, and you can see it sort of highlighted there in orange, and it produced a thermal plume with a limited extent, and that's largely because of in this area of the Lothians we have quite steeply dipping coal fields, coal seams, which limits the groundwater flow and reduces the lateral extent of that plume. So it's fairly limited in extent. You might think at first glance, okay, great, that plume is right next to the Easterbush site, so that would be the best place to use the waste heat. But actually, we kind of realised that because it's a relatively low demand at Easterbush, it's actually more financially viable to concentrate on the larger demand at Lonehead to the north. So yeah, that's what this talk is focused on, really. So to understand the techno-economic aspects of this, we kind of defined three scenarios, which I'll go through in turn. For each of these, we did a sort of conceptual design, costed it up to give the capital and operational costs, and then determine the levelized costs of both cooling and heating. So for those not aware, that's the total lifetime expenditure divided by the heating or cooling that the system delivers. So our first scenario here is the direct waste heat connection, and this just involves essentially a pipe connecting at surface the data center to the network, so no involvement of mines. And because there's no mines involved, that obviously reduces the capex associated with drilling. But as you can see here, we've got this graph in purple. You can see the waste heat supply at 6 megawatts throughout the year, but the demand of our proposed Lonehead network actually varies quite a lot throughout the year, as you would expect, with seasonal demand variation. So it's not actually that well matched to the heat demand. So the idea is where you can, you use the direct waste heat from the data center. Great. But at times when the demand is greater than the ACF 6 megawatts, you have to rely on quite significant peaking plants. So this is low efficiency electric boilers or air source heat pump, or something with a fairly low coefficient of performance. And then on the flip side of that, in the summer months when there's there's not a demand from the network. You need some alternative cooling methods for the data center. So that's either free cooling using the ambient atmosphere, or if the temperature is too hot, you have to revert to mechanical chillers, or air conditioning units. And you can see here we've calculated the levelized costs of heating and cooling. I'll just say the business as usual row you see there. So for the cooling, we define that as what the ACF currently use, which is predominantly atmospheric free cooling. So using where we can the ambient temperature of the outdoor environment to cool the data center. But there's also some reliance on chillers when the temperature gets too high. And in terms of business as usual for heating, we assume that there's sort of gas boilers in every home. So yeah, you can see that. You can see that the levelized cost of cooling for the direct connection is actually very competitive, and that's because we've assumed that the heat network operator, or the third party that comes in and constructs the heat network, would pay for the infrastructure, and in return get sort of the cooling from the ACF free, because it's just waste heat. But you can see in terms of heat, you can see that it's quite a bit more than the business as usual, and this comes down to the significant reliance on peaking plant, which obviously drives up the operational costs. So, quick drink. So case 2 is the geo battery. So this does involve the subsurface. So we inject heat into the mines. The groundwater flow carries that downstream to a mine water heating scheme at the point of extraction for the heat network. So you can see the nice 3D modeling on the right here, and you can see all the mine workings and things. But we need to do this 3 abstraction and 3 discharge boreholes for each system, so 12 in total. We actually want those boreholes to be located fairly close together, because you want the thermal plume that's created by the cooling to be picked up, if you like, by the heating scheme. So you want a kind of element of thermal feedback, if you like. And the geo battery acts as this huge thermal store, which obviously reduces the requirement for peaking plant. And that's reflected in this levelized cost of heat here. So you can see really already big drop in the levelized cost of heat, much more competitive with gas, because there's much lower reliance on that peaking plant. Our third case here is MTES, or mine thermal energy storage, and this is a bit of a hybrid approach, if you like. It's kind of best explained with reference to this graph again. So the idea is that you use the direct waste heat connection when the heat network demand is well matched to the heat supply. When it's not, you rely on boreholes and the ground, tap into that thermal plume that's replenished by the data center waste heat. And in the summer, you don't need to rely on alternative cooling methods. You just dump that heat to the mines. So overall, there's a lot better balance of supply and demand, and there's only a minimal reliance on peaking plant there. And because you're using the direct connection when you can, there's fewer boreholes required. So this is lower capex, lower pumping costs, and the result of that, as you can see, is we end up with a levelized cost of heat that's actually more competitive than gas, which is great news. So just putting these all together here, as I said, the cost of cooling is very low, because we've assumed the heat network operator absorbs most of those cooling costs in exchange for getting the waste heat from the data center free of charge. And the levelized cost of heat in the bottom here in these purples, you can see that the direct connection is more expensive because of that imbalance in the supply and demand, whereas actually both subsurface geo battery and MTES options do have quite a strong feasibility, with the MTES actually winning out because fewer wells required, as I said, and especially at this site, because the water level is about 100 meters below ground level. That's quite a considerable pumping cost that adds to the OPEX element of the cost. So I'd just like to finish very briefly on where we're hoping to go next with this research. And really, the idea is to find the best place to do this within the country and perhaps even internationally. So just in the UK first, here's a map, and we've seen a similar one this morning, but the distribution of data centres around the UK. And you see that while most of them obviously focused in London and the southeast, still about 20% of them overlie coalfields. So what we started to do is just at a very high level sort of screen temperatures and transmissivities and things to give an idea of where the best coalfields are for this kind of thing. So yeah, we looked at temperature, proxy for depth. We've also looked at high level idea of the structure. So remember I mentioned the loadings are quite steeply dipping, which limits how far the plume can go. So perhaps flatter strata in the east of the country might be better. And we've also, again, high level, looked at transmissivity and perhaps how fast those plumes can move. And with kind of early indication is that perhaps central Scotland, the northeast, where we are right now, and Yorkshire could be potentially good candidates. And then very briefly, just finally, I guess there's an international perspective to this. And there's this interplay of climate and where you might not be able to do free cooling in these hotter climates. But also we need to think about the limitations of this, like that there will be a limit to how big a data center can be cooled with these gigascale things. I think it's not trivial to cool these. There is a upper limit, so we need to sort of explore that. And as well, what plays into this is regulation on heat reuse that exists in some countries, perhaps carbon credits as well. And in these areas, it's kind of where cooling only revenue streams perhaps become more viable, and we don't have to pair it with a heating scheme to make it viable. But yeah, that's all I had to say. Thank you very much.